I would like to begin by thanking the Stride fraternity for giving me the opportunity to be part of the faculty success stories. I am Apparao. I moved to Clemson University in year 2000 during the fall semester. I am currently the Robert A. Bowen Endowed Professor in the Department of Physics and Astronomy at Clemson University. I'm also the founding director of the Clemson Nanomaterials Institute. I was privileged to be able to serve for one term as the Associate Dean for Discovery in the College of Science at Clemson University. At that time, I endeavored to amplify research impact across several disciplines at Clemson University. Before moving to Clemson University, I was at the Center for Applied Energy Research at University of Kentucky. And it was at University of Kentucky that I earned my PhD working in the field of high temperature superconductors under the supervision of Professor Peter C. Eklund. Okay, in general, the purpose of any research, I believe, is basically consists of three things. First is we want to expand our knowledge, and then we want to understand that knowledge, and finally leverage that knowledge for the benefit of society. I was at the University of Kentucky, and as we know, Kentucky is a coal state or a coal mining state. The Center for Applied Energy Research, where I was employed in Kentucky, is very well known for coal research. And during my tenure at CAER, there was growing awareness of the greenhouse gas emissions and their adverse effect on our environment, and the need to reduce our dependence on fossil fuels. Beyond coal, even gasoline comes into that category. So one of the options was to try to develop renewable energy technologies like solar, wind, hydropower, geothermal. But there seemed to be an insurmountable challenge for renewable energies to be able to take off and displace fossil fuels. Why? Because fossil fuels are so good that they deliver a huge amount of energy density and power density. So how can we change the game here for renewable energies? So following many discussions and debates at the national, international level, basically the federal government came up with this National Nano Initiative in the year 2000, or NNI. And the basic goal of NNI was to be able to give researchers the chance to control matter at the nanoscale so that unprecedented materials properties can be elicited, and those properties can then be used to create revolutionary technologies that benefit the society. The materials at the time before NNI were incapable of changing the game for renewable energies. And that's why, for me, it was very fortunate that when I moved to Clemson, NNI was also launched by our federal agencies. And I did ride this NNI wave, got a lot of funding through NSF, and helped me build a strong research group at Clemson University. When I looked at the different opportunities under NNI, it was very obvious to me, because of my background in carbon at Kentucky, to be able to explore carbon nanomaterials with a view towards developing them for renewable technologies, specifically energy harnessing and energy storage. What was the motivation for me to enter the research field? I was very fortunate during my final year in India to be able to do an internship at one of the leading research institutes in India. It's the Baba Atomic Research Center, which is located in Mumbai. And the projects that I worked on at Baba Atomic Research Center gave me immense joy, which I did not derive before from academic work. So that motivated me to become a scientist. And more importantly, it brought me to the US for higher education. And at the University of Kentucky, when I joined Professor Eckland's group, he introduced me to the field of spectroscopy. And I fell in love with it immediately because it allowed me to actually watch quantum mechanics in action. And that piqued my interest, my curiosity, and enhanced my love for learning. And I could begin to appreciate how spectroscopy can be used as a complementary tool to study underlying physical phenomena. For example, when you have a superconductor, the superconductor, you cool it down below what we call the superconducting transition temperature. And at that temperature, the charge carriers in the superconductor do not feel any resistance to their flow in that material. In order to do that, we attach leads to the superconductor and we start and cool down the sample until the resistance reaches zero. And that's how we study that. But if you are a spectroscopist, you can simultaneously also look at what other things are happening as the resistance plummets to zero. For example, it is known in superconductors that a superconducting gap opens up. And spectroscopy is a very neat way of exploring or studying that in the same experiment without any additional sample preparation. So it was pretty exciting to learn that spectroscopy is a very powerful tool, which I use even today. I also developed passion for research after working with Professor Mildred S. Dresselhaus at MIT. She was my mentor there. She is a pioneer in the field of nanomaterials research and a legendary figure in the field. She's known as the queen of carbon. And besides nanoscience and nanotechnology, she actually taught me great lessons for life, which I use even today. One of them is that there is no substitute for hard work or self-discipline, and she exemplified that. And specifically, if you want to excel in research and development and translate that to the market for societal benefit, we need to have a very strong work ethic. And she was very famous for that. She was also very well known for her kindness and generosity. So both Professor Eklund and Professor Dresselhaus are my guideposts, and they help me tackle complex and challenging situations I find myself from time to time at Clemson University. So I just pause and ask myself, what would they do or how would they deal with a particular complex situation? And that has been very helpful in my career growth. And so when I look back at my own journey, that motivation basically led me to establishing the Clemson Nanomaterials Institute so that the next generation researchers can benefit from a similar ecosystem that I benefited when I was at the Baba Atomic Research Center in India. So why carbon materials? I liked carbon materials or began to work with carbon material because carbon exhibits multiple bonding states with itself. So you can make an entirely carbon material with a wide spectrum of properties. For example, the lead in our lead pencil is the amorphous form of carbon. It is very cheap, as we know, and it can easily break. You can just break it with your bare hands. It has very poor mechanical property. Then carbon can also rearrange itself with five other carbon atoms to form what we call a hexagonal ring. And these hexagonal rings are usually in a plane. And those planar sheets of hexagonal rings, when they come together, form what we call graphite. And these planes are held by van der Waals forces, which means, these are not very strongly bonded, and though they can slide with respect to each other. And therefore, graphite is a great lubricant that is used in the industry, for example. And then the opposite end of the lead pencil or amorphous carbon is a diamond, which is also made out of carbon, but it is one of the strongest materials. So I was fascinated by the fact that, you can have one element, carbon, and materials made of carbon with a wide range of properties. And or just a decade before 2000, around 1990s, new forms of carbons were also being discovered, which are known as fullerenes. They are basically carbon atoms that form closed cage structures. And there are also other forms of carbon where they basically, you take a sheet of honeycomb lattice carbon and you roll it up into a tube to form what we call a carbon nanotube. And then planar sheet of hexagonal honeycomb lattice of carbon is a graphene. And more recently, there is also another form of carbon which is called Q carbon. So these all new forms of carbons are called as carbon allotropes. They offered a wide range of materials for me to sort of investigate. So regarding defining research translation from a market perspective, I would compare research translation to like building a bridge. I would actually imagine that to be a bridge between the academic research and the real world application. And as is the case with building a bridge, you have to take into account of several factors. The environment in which the bridge is going to be built. Is it going to be built over an interstate or over a water stream or what have you? So that basically then defines the design principles and the engineering complexity. Then, of course, we have to worry about the budget constraints, what funding level we have, and how that bridge can be built safely and how it can be used safely after it is built, and how long will it take to build that bridge. So all these are important factors that research translation capacity at a university can be increased when we pay attention to these kind of important questions. Of course, the real world applications are not in our control, but however, the academic research is our cup of tea. That's why we are at this university. So when I look at academic research, I see that there are at least two broad categories of academic research. One of them, I call it the blue sky research. Basically, the PI launches into that research for just fundamental sake, for curiosity. Namely, that kind of research may not lead to any applications. A classic example of that is discovery of gravitational waves, which was predicted by Einstein at the start of the early 1900s, and it was directly detected or measured using interferometry in 2000. So it took about a century. So that kind of time frame is not what academic researchers can aspire to work on and then bring their research to translate to markets for real world applications. Another example of blue sky research is quantum computing. Peter Shor in mid-90s published an algorithm that carries his name, and it sparked the exploration of using quantum mechanics for quantum computing. And the potential was huge because it could revolutionize many fields. And as we know today, quantum computing is indeed a reality, and it took a couple of decades. So that's more like paying attention to the time frame. And the other side of the blue sky research is what I call applied research or problem-driven research. And I've been very fortunate to have many industrial collaborators fund my team to carry out projects that are of interest to them. And those are typically 3 to 6 months, very short time frame. And at the most about a year because they are very goal-oriented and they need a product that they want to take it to the market. So for any university to have a broad translational impact, I think the points I just mentioned, using bridge as an example, must be taken into consideration. The main challenges for translating my research into the real market, real world market, I would say there are basically three tiers of challenges to translate research to the market for societal benefits. Given all the tasks that a faculty member performs at a university, and I think the most difficult commodity is time. Finding time to devote to the research that has market value and translate that outcome from the research lab to the market is very difficult. We all have 24 hours in a day. And so if a faculty member embarks on translating his research to the market, then something else has to give in terms of his other academic duties. A related challenge is the time frame it takes to translate the research. As I mentioned, market-related projects generally are on a very short time frame. And can this faculty member carve out such, a short time frame to focus on translating his or her research to the market? And this is very difficult because in academia, we are quite used to having research projects that take a couple of years, not a couple of decades, couple of years, because we train PhD students, and typically PhD dissertation lasts anywhere between 4 to 6 years. So finding time and being able to carve out a time frame in which the project can be accomplished is challenge number one. At least that's the case for me. And the second kind of challenge is also one has to pay attention whether there is a need for the product that you want to translate to the market. Does the market need it? And do you have the resources in terms of equipment, in terms of funding, manpower, and so on? And the third challenge is also what is the current competition for the product that you want to launch into the market? Is there awareness for the kind of products that you want to bring to the market? And because customers are usually skeptical and have a huge inertia adopting to a new technology because its nature is unknown to them. And so, but fortunately, for us at Clemson, we have STRIDE, and we also have Clemson University Research Foundation that helps faculty members deal with such challenges. As I mentioned before, the National Nanotechnology Initiative allowed me to embark in the carbon nanomaterials research. And in early 2000, at that time, what I found was that procuring nanomaterials was a huge challenge and very cost prohibitive. And so the first strategic direction that I took was to be able to develop synthesis methods where these carbon nanotubes, in my case, can be made in bulk quantities and in high purity. That means we wanted to come up with a synthesis method that would create carbon nanotubes, high quality carbon nanotubes from milligram level to kilogram level, which was a big step forward in around year 2000. So we developed a method which we call liquid injection based chemical vapor deposition method. And the basic idea was to have a hydrocarbon source or a precursor. In our case, we chose xylene, and a catalyst in the form of a salt. And in our case, we chose ferrocene. And we would simply weigh the right amount of ferrocene, mix it into xylene, stir it up. Xylene readily allows the ferrocene to dissolve in it, and then we would inject it into a hot reactor. And basically what would happen is that the hydrocarbon would disintegrate, and the catalyst particles would form a nano-sized catalyst particle. The carbon would dissolve into it and precipitate out in the form of a tube. So we called our method a step closer to realization of carbon nanotube production. And in our case, we basically grow forests of carbon nanotube, meaning that the nanotubes grow right next to one another, resembling like a forest of trees that we find in our state of South Carolina. So my students, after they graduated, took that technology to the market and they established a company. They have done very well, which is today a multi-million-dollar enterprise. The liquid induction chemical vapor deposition method that I just spoke about is also interesting from a fundamental standpoint, meaning that, the method I just explained grows vertical nanotubes. They grow like a forest of nanotubes. But then one could play with the composition of the catalyst and make these nanotubes grow as a spider, or we could make them grow like a branched shaped nanotube, like a Y branch or a T branch. So they would grow for some time and they would branch. And both the coil nanotubes and the branch nanotube had many implications for the market. In collaboration with my colleagues at University of California, San Diego, we showed that a branch nanotube acts like a nanoscale logic gate because you could use it as a drain, source, and the gate. It has three prongs. And the nanosprings, the bed of nanosprings could be used for providing impact protection for microscale electronics. And that was one of the technologies that Clemson University licensed some time back. So basically, in short, while establishing a continuous production of aligned carbon nanotube manufacturing, we also established a function follow shape research paradigm for carbon nanotubes, meaning that there is a close relationship between the physical form or the structure of the nanotube and the way it works, whether as a bed of cushion or nanosprings or as a nanoscale logic gate. Apart from the carbon nanotube synthesis, the liquid injection method I just spoke about, a significant milestone in my research is the use of Raman spectroscopy as an inline characterization tool for carbon nanotubes. So my study of carbon nanotubes using Raman spectroscopy is a perfect example. It started out as a blue sky research project. All we wanted to do is to understand what happens when you take a plain sheet of hexagonal carbons and you roll it into a seamless tube. How do the vibrational properties, the electronic properties of such a tube change, get modified from that of the planar cousin? And to our great surprise, we discovered that the energy of the electrons that move in the circumferential direction of the nanotube. So if you imagine a tube, the electrons, those move along the circumferential direction, their energy is quantized, much like the electrons in an atom, if you recall the Bohr model for an atom. And the upshot of all of that is that basically when you create these nanotubes, we could basically tune the frequency of the Raman laser and couple to a tube of interest without having to separate the tube from the rest of the tubes. Because separating a nanotube, as you can imagine, is a Herculean process. It's not easy. You cannot pick it up. You have to have special toolbox in order to do all that. So this discovery of quantum confinement of the electrons that move in the circumferential direction gave us the capability of studying each tube by tuning the laser frequency. And moreover, we could also tell from the shape of the Raman profile whether the tube was metallic, whether it's a semiconductor, and if the tubes were doped, like with alkali metals or any other element. For example, you could substitute carbons with nitrogen and boron, and you could make them superconductor, and so on and so forth. So we could tell the dopant concentration. We could also tell if the tubes were defective, if there were any tubes in that, any defects present in the tube. So this ability of using spectroscopy was realized by the industrial partners, and now it is a inline tool for studying the amount of carbon nanotubes that are present, or the quality of the nanotubes present, let's say in composites or in microelectronic devices, and or coatings that are used to make electrodes for batteries, supercapacitors, and so on. So my recent milestones include bringing silicon into battery technology. Without going into a lot of details, silicon vastly improves the battery performance when it is present in the battery electrodes to the right amounts. And so we actually created a new form of silicon, which we call silicon nanoquills. It's a patented technology done in collaboration with my colleagues here at Clemson University. And we also worked with commercially available silicon and created technologies that encapsulate that silicon in a carbon cloud. Again, work done with my collaborators here at Clemson University. And both the silicon nanoquills and the silicon with carbon cloud are perform much better than commercial silicon as far as battery performance is concerned. And another milestone is the demonstration of a device which we call TRECO, TRECO, which is basically an acronym for thermally rechargeable electrochemical oscillators. So this is a device that my team developed, which has the ability to convert low-grade waste heat into electricity. And it does it very efficiently. It has a thermal power, which is 4 times the record thermal power that's in the literature. And a patent has been filed for this device also. Moving on, there are 2 more which I would like to mention. One of them is photo-rechargeable supercapacitors done in collaboration with researchers in India at the Indian Institute of Science. Basically, these capacitors exhibit an increase in capacitance with an increase in current, which typical supercapacitors do not. And the potential for these photo-rechargeable supercapacitors is that they can lead to fast charging, energy, and power-dense supercapacitor. And lastly, I like to mention that we also developed a technology where we can take agricultural products or co-products and then convert them into very high-grade activated carbon, which has applications in supercapacitors, water filtration, and so on and so forth. So these are some of the recent milestones. How do you approach difficult decisions in your research? So in my research, basically, the first thing I ensure is that I do have the right infrastructure in terms of workforce, funding, equipment, and the right composition of the team, which is also very important. And like I mentioned, the time frame over which that project needs to be completed. So establishing a timeline for project delivery is crucial. And having all these essential ingredients, then you basically roll up your sleeve and get to work. And as the project progresses, the way I handle these challenges is to be able to meet with my team on a weekly basis and come up with go, no go decisions so that the project is moving in the right direction. And the other important thing is that we basically try to get out of our comfort zone. For example, sometimes we have to change the composition of our research team so that we don't have any weak links in the chain, and be very bold and also invite collaborators whose expertise is not in the field of your research. And often we found that they bring a different angle to the project and to the project success. So lastly, despite doing all this, projects still do fail. And when they fail, I basically tell my team to look for outcomes that are meritorious, although we did not achieve the desired goal. So this is what I call having a plan B in the hip pocket. So then there may be a possibility to basically build up on the research outcomes that are still meritorious for another purpose. What advice would I give to other researchers? I would say follow your passion, be bold, take calculated risks, and see where your research takes you, and agree to projects that have a reasonable time frame. Don't stress yourself out. Focus on what can and cannot be patented and licensed. That's the other thing. I spoke a little bit about the discovery of gravitational waves, right? And so gravitational waves or even quantum computing, those cannot be patented because those are natural phenomena that exist. However, the tools that were used to discover, let's say, gravitational wave, basically an interferometer, is patentable technology, right? So we have to be smart enough to realize, what portion of your research can be patented or licensed. And so that's what I would tell anybody wanting to get into translating the research to pay attention to those kind of details. And keep in mind always, who would benefit from your research? Who are your potential customers? What is your competition? So on. And if you succeed in identifying a clear societal impact that your research can bring, then regarding that knowledge, start filing invention disclosures, file for patents, etc., and communicate effectively so that without any jargon. So the value that your translational research brings to the society is appreciated, and leverage the social media for that. And finally, if you have time, if you can devote time to start up your own company, that's great. And ensure that your startup company has a proper mix of technical staff, administrators, and business savvy team members. All are critical for the success of your startup.